So how many people have heard about tungsten fabric? Okay, only few. How about contrail? Still few. Okay, so so I'll give a very quick overview of what tungsten fabric is. I'll walk through the architecture of it, and then I'll cover how we do the edge computing or the remote computing using tungsten fabric, and then I'll get into the edge stack. Like in the introduction you mentioned, I'm on a technical advisory board for the Linux Foundation's Edge program. So I have a few slides from them. I'll talk about overall Edge programs, and then I'll talk about the Akraino Edge stack specifically, and then I'll talk about how Akraino and Tungsten fabric together are trying to bring several integration projects. So having said that, let's dive right in. Oh, this thing doesn't work, looks like.
You might need to plug in the USB there.
Okay, so I'll have to click here then. Oh, this won't work. We need here. Better. Okay.
No, not right. The other way. No, sorry. That's probably...
This one?
Yep.
Okay,
there.
Good. All right, thank you. So from the high-level architecture point of view, the way tungsten fabric works is, if you look at the top right side of the slide, so the logical view works like that. The whole policy management and the whole logical view is you have multiple networks, and in those networks you have ports, so I'm keep getting a signal to stay here. I like to get into the middle of that, but that's okay. I'll try to stay here. So, so the basic concept is you have a bunch of virtual networks. You create a port, and you put the port in a network, and you can attach anything to that port, be a virtual machine, be a pod, container, bare metal machine, or even a top-of-rack switch. It will manage anything which you connect to the port. So that's what logical view is, and then you can define the policies around those networks, around those workloads. You can specify how they are allowed, how they can communicate, and then you can specify the services in between. So whether the firewall or any other services you want to introduce. So that's a high-level logical view, 50,000 feet. This is how it works. Now, when it gets to the nitty-gritty, then the guts of the system. So on the top left-hand side, what we have is the main controller, which we call it a tungsten fabric or a contrail controller, right? And the key components are config, control, and analytics. And what it is a single place where you can create the configuration. Doesn't matter how geographically distributed your deployments are. It's a single place where you can configure the things and manage things. Okay, and the control plane is distributed. And now at the bottom right-hand side and the left-hand side, on the right-hand side, you will see a bunch of hypervisors, right? And that's where VRouter runs. Tungsten fabric is a VRouter based architecture. It's a layer 3 architecture. So there are no, you don't need any other additional routers. So routing is everywhere. As long as the networks are defined, you never need to create routers or anything like that. You simply specify the policy, which network or which workload is allowed to communicate with which workload, and so forth. Okay, so these hypervisors, they can be sitting in a same rack. They could be sitting 20 feet apart. They could be sitting 2 miles apart, 20 miles apart, or 2,000 miles apart. Doesn't matter. The control plane talks to the VRouter agent, which runs on a hypervisor, And VRouter agent essentially manages all the policy framework, right? The VRouter agent, I'll touch bases with that in a minute in my next slide. And up there, I don't know whether the pointer works or not. No, it doesn't. So up there on the controller, you will see on the right-hand side, there's a BGP dot. So we use BGP for peering, so you can scale it horizontally as many control nodes you want to deploy as possible. And that's what makes this architecture extremely scalable. There are customers who are running in excess of 25 million customers in production. In other words, it can scale to a very, very large number. There are providers, very large providers, who are running 30 to 40,000 servers using this in production. So that's what makes it very, very scalable. So it gives you flexibility to move your workloads any which way you want. You can move you can put any kind, like I mentioned, any kind of workloads. So when you have bare metal machines don't have hypervisors, they don't have VRouter, so they connect to the Tor, and that's on the left-hand side of the picture. So when a port, again, the view is the same. So you have a red network, for instance, you have a bare metal machine or a Tor. The fabric management and underneath, under the covers, it automatically figures it out where and how to communicate with things. So it will automatically use netconf to configure those bare metal machines. So it's a single pane of view for regardless of how and where the workloads are. And the final piece is the gateway. The gateway is the critical part. So again, it uses a BGP control plane and basic IP fabric. And this is how you get in and get out. And this is how you scale it to any levels you want to scale. So that's a high-level view of the Tungsten Fabric's architecture view. Okay. So now here I talked about the logical view. So here is just a quick example of how does that work. So say you have logically defined a policy up there. So you have 3 networks, green, blue, and yellow. Those are the workloads, G1 through 3 and B1 through 3. So those are the workloads you have defined, and your policy states that allow HTTPS traffic between those 2 networks, between G1 and G2 in this example, right? At the bottom layer, this is where the actual deployment is. That up there is a logical view. So you're saying that G1 and G2 HTTP traffic is allowed, whereas in the bottom, they could be sitting far apart, or they could be sitting anywhere. So what happens is the VRouter will look at it, and based upon the policy, it will move the traffic, it will forward the traffic over the IP backbone and deliver the packet where it needs to go. As another example, if you say from G3 to B1, which happens to be on a different network, and you say don't allow non-HTTP traffic. So at the bottom layer, you will see they happen to be on the same hypervisor. So we don't care where the workloads are. Depending upon where the workloads are, VRouter will figure it out and will apply the policy and will either block the traffic or it will allow the traffic to move. So notice, this is happening at a workload level as well as at a network level. Okay. So here is another example. So inter-network traffic traversing is a service. So you want to insert a service between these 2 workloads. At the bottom layer, they happen to be sitting on the same hypervisor, and the service happens to be running on the same hypervisor. So VRouter will automatically route the traffic through the service, and the service will decide whether to allow the traffic to move or not. So that's a high-level logical view. So everything in the Tungsten Fabric networking, that's how it works. So essentially, as a provider, you're essentially writing a bunch of policies. You're defining how your workloads are placed, what kind of workloads are. Rest of it is managed for you. Here is a quick overview of the VRouter architecture. So VRouter has two components. The one is the actual forwarding engine, which by default sits in a kernel, and this is the one which is encapping and decapping the packets and is putting it on the wire and receiving the packets from the wire. And based upon it's a VNI or MPLS label, it is forwarding to the appropriate routing instance, and that's how the traffic moves in and out of the workloads, right? And on the top side is a VRouter agent. That's the sort of a brain. VRouter agent, in my previous slide, I showed that the VRouter agent or the hypervisor is talking to the control plane. The control plane parses the policies, it looks at the policies, it figures it out where the agents are, or it needs to broadcast, or it needs to talk to a specific agent and whatnot. That information gets passed to the VRouter agent, and VRouter agent locally is actually rendering those policies, and based upon that, so essentially it does three critical functions. The agent, it's a proxies for DHCP. This is the agent which is responsible for providing IP for the workloads, and ARP and DNS services, right? So that's a high-level view. So there's a lot written here, but I'm going to just walk through quickly. So in terms of deployment model.
Before you proceed, one question: is it a mesh network or point to point when you do in the BGP in there, the previous to previous diagram?
So
That's not this earlier one.
Which one?
Previous to this diagram. Yeah, here the links which are shown, the green ones, lock to lock. Is it peer to peer? Or is it a mesh network? Or
no, it's a peer-to-peer. It's a pointed traffic. You're moving. You're sending. Say you're doing a ping, or you're sending a TCP traffic or UDP traffic or whatever traffic is. Two workloads are talking, and you have defined a policy. Policy dictates how the packets flow.
Thank you.
So, sorry, I went too far. So there are 4 deployment models for the VRouter. By default, it's a kernel VRouter, which is what I described earlier. So the VRouter itself sits in the kernel module, and the VRouter agent sits in the user space, and you have workloads, and the packets flow through the VRouter forwarder. The second deployment model is a DPDK. If you have applications which demand high throughput and they can support DPDK, you can use DPDK model. In this case, the VRouter runs in a user space along with the rest of the applications. A third model is a hybrid model where you can use VRouter in kernel as well as SRIOV workloads. If you have a VNFs, which can take advantage of throughput by using SRIOV workloads, so you can deploy that model. So that's available for you also. And the fourth model is a SmartNIC model, where you completely offload the CPU from any VRouter functionality, and you move it all on the NIC, and that gives you the highest possible throughput. And for some of the edge use cases where high throughput and low latency is the requirement, so that becomes the choice for deployment. Okay, so that was what I described to you was essentially virtualized workloads. I used those, and the Kubernetes works or containerized workload pretty much work the same way. The bottom picture looks a little different, but these are just 2 hypervisors, like in the very first slide which I showed. On the top right-hand side, the Contrail controller and analytics, which I showed in the previous big architecture document, it's still the same. So what we have created is a Contrail Kube Manager, which listens to the API server and essentially does what was being done in the virtualized workload for the same as Kubernetes workloads. So here is a quick example of if the user does kubectl to launch a pod, right? So the API server talks to the Contrail Kube Manager. So here you're launching a pod create, and that request goes to the controller, or if you're doing an update or whatnot, so it goes to the pod, to the controller, and at the same time, the scheduler picks which hypervisor is going to place the pod at, and goes to the kubelet, and in parallel at the same time, based upon what I described earlier, the control plane is talking to the hypervisor and is passing the information down to the VRouter agent on the hypervisor. That's the right side of the path. So the Contrail or Tungsten fabric is essentially pushing the policies, because you still have the same network. All we've done is just a different type of workload. So the policy framework is exactly the same. Everything is the same. So that policy framework is getting pushed while the scheduler is trying to place the pod there, right? So everything is ready in the VRouter at the same time, and we have a CNI plugin, right? So kubectl talks to the CNI plugin to plug the routing. It will talk to the VRouter agent. VRouter agent will at that point provide the IPAM. It will give the IP address for the pod, and the networking gets plumbed, whatever needs to be done, and the call goes back. So essentially that's the flow, which is very similar to, if you're familiar with OpenStack world, the way Nova and Neutron works. So the Nova is talking to the L2 agent and is placing the VMs, and at the same time it's talking to the Neutron, and the networking is getting plumbed. It's very similar, very identical flow here. Okay, so Tungsten Fabric's evolution to microservices. We started with the virtualized machines as well as bare metal machines. Over time, we fully containerized it, and now we have full microservices deployment. So I don't need to talk details about why microservices are beneficial. Everybody knows that. So we take full advantage of microservices architecture with this. Now, here is one thing which is very powerful in Tungsten Fabric, which I don't believe I have read anywhere anybody else doing it. So multi-tenancy, levels of isolation. What do I mean? So on the left-hand side is the default model. If you deploy Kubernetes, everything is a flat network. Any tenant can talk to any tenant, any workload can talk to any workload. So here, namespace, think of namespace as a tenant. So you have tenant A and B. They're freely communicating with each other. Their workloads are talking to each other. So there's no isolation. Okay. If you use network policies in Kubernetes, you can achieve multi-tenancy by saying namespace C or tenant C and tenant D, they can only talk among themselves within their workload, but not across each other. That's the best you can achieve with Kubernetes-based deployment. What we have done is we have pushed it to further and taken the isolation all the way to the pod level, where you can not only you can say I want a full multi-tenancy, you can say even within a given tenant who's allowed to talk to who. And if you remember the previous slide where I walked through the packet path, and I was showing an example of a given workload talking to a given workload, whether they're in the same network or a different network, it didn't matter whether those networks belong to the same tenant or a different tenant. It doesn't matter. We can do it at a very granular level. So that's That's what I mean by levels of isolation, which we offer. Okay, so that was a basic high-level architectural view of how Tungsten Fabric works, right? So now having described that, now I'm going to start walking towards the edge. So whatever so far I talked about was that applies to everything, the central data center or so I have 30 minutes. Okay, so I'll try to speed up. So what we have done is we've taken, if you look at the top part, it's no different than the controller, which I showed in my very first slide. So all I'm doing is I'm just breaking up the components a little bit more so that they stand out. So you have a config, you have analytic database, and then you have a VRouter. And one thing which I've done is I've taken the control. It was a block up there in the previous slide. So what I've done is I've taken the control, stretched it out, and made it distributed. And I said, okay, I can leverage MPLS backbone, and I'm going to spread it out, and therefore I'm going to carve out multiple POPs. So the VRouter still runs in your central location, as well as it can now run into the secondary POPs. So that's how we start to stretch. Remember in the very first slide I said it doesn't matter where the VRouters are, where the hypervisors are. So essentially I'm taking that concept and I'm sort of putting an envelope around it, and I'm calling it as a POPs. So now I can place these POPs anywhere as long as they have a connectivity through the MPLS backbone, right? So here is an example. In a standard Contrail or Tungsten Fabric model, what you do is, what we do is, so you have a MPLS backbone, and there you have a gateway. Remember in the very first slide I talked about the gateway, that's how we get in and get out that's how we move the traffic in and out. So on the left-hand side, so what we do is we take the prefixes which are coming from the MPLS backbone, and we map it to the workloads in the Contrail world, and the reverse is true. However, with the distributed or with the remote compute model, what we have simply done is we have created multiple prefixes depending upon where the compute lives. So on the left model, we don't care because it's a one central model. So it's assumed all the compute is available at one place. So now that the compute is distributed and each compute has a different gateway, so we want to compute different prefixes, and therefore we want to map those prefixes. So that's how, so I'm sort of walking you through how we essentially take the same architecture and expand it. So what it gives you is in a standard deployment, if you have workloads which are being managed by Contrail, and then you have a non-Contrail site which is trying to talk to the local site, you could potentially trombone the traffic. You could move it, we could take a longer path because this is standard routing. Whereas with the smart prefixes, because of the source-based, we know, destination-based, where the compute is, and we can therefore create smart prefixes, and we can move the traffic appropriately. Okay, so now, so the challenge comes that now, okay, fine, we have multiple POPs, we have multiple gateways. How do I say that which gateway is what? How do I compute the prefixes? So that becomes the challenge, and that's what we have to solve in order to achieve this, what I'm describing here. So what we do is we distribute the control plane logically. We keep it, everything still runs in a central location. If you notice, all the components are still up there, right? But logically, we have carved out. So the gateway function is there, and the VRouter, what we're talking about, the XMPP traffic, where where the control plane is talking to the VRouter agent, right? So now they are sitting in different places, and we have the gateways. Now these gateways could be in a one cloud, second cloud. It could be in your remote site, somewhere in a central office. Doesn't matter where they are, right? If it is let's say it's an AWS, we are using the gateway function at the AWS. If it's a Google Cloud, we're using that, and we're building the paths through that, and that way we can achieve it. But everything's still sort of central, but the control gets distributed. Okay. So now, once we do that, how do you configure this? So all of that is architecturally cool, but when you want to deploy it, how do you specify which compute is where? So it's like kind of Nova compute zones. So like you have multiple zones. You want to define, okay, this is my zone 1, this is my zone 2. Similarly, now here you're trying to define the edge sites. So what you do is, what we have is, we call it as a subcluster concept. So you come in and you create, to deploy what I described so far, it may sound very complex, but it takes 2 or 3 configuration commands. That's all. That's all it takes, and everything else, all rest of the magic takes place automatically behind it. And what you do is you simply specify that which compute nodes are going to be in POP A, which compute nodes are going to be in POP B, which compute nodes are going to be in POP C, and we will automatically launch the gateways, and you provide the credentials where the gateways are, like which cloud or which place or however, right? So what happens is, so you essentially get a complete slice, a logical slice. You have a VRouter functionality, you have a dedicated POP control, and you have all the other functions which I talked about it, and we create the gateway. So now we have carved out like 3 essentially slices for you. So what you get as an end result is you get 3 independent routing domains. So what you have is you have one domain here, which is by itself a complete deployment of an edge site. You have on the left-hand side another deployment. There you have a redundant VRouter. Here you have a single VRouter, and then you have one default cluster which is sitting up there. Now what that gives you is, it gives you independent routing domain. What does that mean? That means now you can reuse the IP addresses. You can, if you're a provider, you can continue to reuse. You can give the same IP addresses to your different clients, and you will never run out of IP space because you're reusing it, as long as these 2 domains are not going to talk to each other. If they're going to talk to each other, then you need to deal with the floating IPs and whatnot. But as long as they're independent, so that it gives you that power. And another thing which it gives you is that I didn't touch the security. Security is one of the key features which Tungsten Fabric offers. So now with this, you get an end-to-end complete security. So you're sitting in your central site, single pane of glass, and you can watch what is going on every edge site, how the traffic is moving, full analytics end-to-end, full security end-to-end. That's what makes it as a really killer use case for the edge deployments. So what that gives you, this is my like a sort of summary of this. So you have a distributed networking for any kind of workloads, virtual machines, pods, and bare metal machines. So one thing I didn't touch on the top right-hand side, bare metal, as well as fabric management. So not only just the Contrail will do the bare metal deployment, it will do the full bare metal lifecycle management using Ironic in the OpenStack. It also does full-blown fabric management. So in other words, if you have top-of-rack switches, you have leaf devices, spine devices, it will automatically configure those for you. Most of the deployments assume that the fabric is already laid out, and they will manage the virtualization on top of it. we go a step further. We'll do the full fabric management as well as. All you have to do is just connect the devices and get away from it and execute few commands, and it will configure everything for you. So what it gives you a full fabric management, bare metal management, Kubernetes support, OpenStack support, right? And you can have a central location, or you can have distributed, fully distributed. There is a whole hell of a lot of advanced networking features which you get regardless of whether you have a small deployment, large deployment. That's why this is the number one choice by a lot of the top tier. Thank you. That's why this is the choice of deployment by the very, very large top tier customers. And this is running in production networks of many large providers all over, right? So now, so having described that, like how we have taken the architecture and have opened it up and we have stretched it to the edges. So how does multi-cloud service chaining, let alone locally? People are having hard time doing the service chaining, and we not only do locally service chaining, we can do across the site service chaining. This is an example. So here, what I'm showing is on your core site on the top, that represents a core site. So you have a service instance, right? And you have two workloads on two different networks, left network and right network, different subnets. So you wanna do a service chain, of course, and that's our bread and butter. Contrail offers that, right? But now I also mentioned with the introduction of this remote computer or multi-cloud, so you can move your workloads anywhere. So now on the same network, remember my very first slide where I said it's a logical view. In the network, so you just define a network, and then you can place the workloads anywhere you want or whatever type of workloads you want. That's exactly what I'm demonstrating here, that on the same network, on a 3 subnet on the right-hand side, and on a 2 subnet on the left-hand side, you place the workloads. They happen to be sitting in 2 different clouds. So now what you have is 3 sites which are sitting in a different domains, right? And we can do the service chaining across them. And the killer use case here is that you don't need to have service instances deployed at your edge site. So you can keep your edge site as light as you want, right? And you can have all your services or all your heavy duty lifting in your central location, and we will take the full leverage of this architecture to do that. I'm not aware of anybody doing that, or anybody can do that, or any other SDN controller can do something like this. And that's because of the way we have architected things. Okay, so this is another thing which I'm going to talk about. This is another very powerful feature of Tungsten Fabric, is the policy framework. So far, I kind of danced around it, that you create these networks and you specify the policies and all that. So I'm going to give you a little bit of an idea of how powerful the policy framework is. So here is an example. So typically, what you will have is you have a deployment where you have a web, front-ending web, then you have an application, and then you have a database. Those are the 3 tiers. And then you have a deployment, staging, and production. So you're deploying that application, you are staging it, you're testing it, and you're putting it in production. That's a typical deployment model for any provider, right? And for each of them, you will have a different policy, right? Because you don't want things, you want to manage it a little bit more in a controlled fashion. So you have 3 policies: policy 1, policy 2, and policy 3. Okay. So what we've said is, why have so many policies? Let's define a single policy and consolidate everything. And I'll give an example in a second. So what that does is it reduces the complexity. It doesn't matter how you're staging and how you're deploying the policies. It's a very simplified management, and it gives you the scalability now, right? So since you have a single policy now, and I've defined it, now I can start placing my workloads anywhere I want, and I can reuse the exact same policy. So now I don't have to worry about defining a policy for Amazon Cloud. I need to use this policy. For Google Cloud, I need to use this policy. For this edge side, I need to use this policy. You define it once, you use it, it works across the board. Everything is done for you magically, right? At this point, I want to ask you a question. If you're familiar with OpenStack, right? If you have a deployment like this with a 3-tier application, and it's a very large, geographically distributed application, let's say you have 100 networks which are carrying your web traffic, and you have another 100 networks which are carrying your application networks, application traffic, and you want to run it through a firewall. Can you think of how many lines of configuration you will write to make that work? Let alone debugging, it will be a nightmare. Here, it takes you one single command, and it will do everything for you. And you can add networks, you can reduce networks, you can scale up, you can scale down, just one command. Once it's executed, doesn't matter how you keep scaling, it's all tag-based. You can create the tags. Here is an example. So here, the policy is allow HTTPS traffic between tier web and tier app, right? So here is your deployment. It says web can talk to app, okay? Now you have a production. It says web can, same policy applies. It says web can talk to app, right? Now what that also means is web can talk to app. Doesn't matter where it is, it can talk to. Now, this may be a desirable behavior, this may not be a desirable behavior. You may want to keep developers out of production sites, or maybe you want to allow it, doesn't matter, it's up to you. Let's say you don't want it, right? So you create a tag, you say match the deployment. If the deployment matches, then only allow. If deployment doesn't match, don't allow. So that's it. So again, still a single command, you're just defining some tags, and rest all would be done, regardless of how many networks, how many workloads are involved, how many, those could be 10,000 servers which you are deploying. They could be sitting anywhere, it doesn't matter, but that's one single command which is taking care of it, right? And now let's make it more interesting. So you have 2 sites, and again, based on that policy, it's going to allow the web to talk to the app, right? And guess what? That web and that app is, again, the same thing. So now it's going to allow that to talk. So that means, so it may be okay because they are both development sites. So maybe you want to allow that. The developers seamlessly should be able to talk to the app tier regardless of where they are. Or you may want to say, no, this goes across some restricted zones. I don't want to allow that. So you simply say match site. So now what you're saying is, if you say you match a deployment, match a site, then what you're doing is you're allowing the same traffic to just go. It's essentially you're controlling how you want to do it, but you're controlling with the tags. You're not trying to configure individual ports. You're not trying to configure individual workloads. You're not trying to configure individual networks. So all the granularity is taken. It's a very high level construct. Here is another example where we're saying that all app tiers should be able to store their data on a local site, not to a remote site. So in this case, you don't use the match deployment. You say any deployment doesn't matter. Everybody should be able to store the data. So that's how the policy framework works. So I just wanted to walk you through to give you a little bit of an idea as to how powerful this framework is, okay? So having said that, now I'm gonna start getting into the edge. Remember I mentioned earlier, I sit on the technical advisory board of Edge. So these slides are LF Edge slides, they're not mine. So I don't wanna take credit for these, right? So I'm gonna just use to describe it. So here we talked about central cloud, all what I was talking about was central, and then I was trying to get into the edge. So why edge computing? So all these applications which are driving the need for edge. They require low latency and high throughput. That's not available in the central cloud. Central cloud latencies can get much higher, right? So that's what's really typically driving the real need for the edge computing. Here are some more granular examples. So I'm not going to go read through them, but this gives you an idea that all of these things which didn't used to exist probably 10 years ago or 7 years ago, they're all coming and they're very dominant players as we go along. And that's what's forcing the edge computing. And that's why edge computing is critical one. Somebody sent me an email saying that within the next 10 years, there will be over 1 trillion devices which will be connected. Okay, I'm getting a flash to speed up. So there will be over 1 trillion devices which will be connected using the edge computing. Hold your questions for a minute because I'm going to run out of time. I'll come back to. I'll take all the questions at the end, right? So let me just quickly go walk through. So here is a survey slide, which this is again an LF Edge slide. Okay, what are the top 5 edge services which are driving the need for the bandwidth? So video content delivery stands out the top, and the autonomous vehicles. And I'm not going to read the list, but you can see that gives you the idea. These things didn't exist in the near past, and they are the predominant applications today. And that's what's driving the need for edge, and that's why it's very critical. Okay, here is another example. So here you have a central data center. Start from the right and let's walk through the left side. So you have a data center which is not an edge. Based on the survey, 70% of operators plan to run VNF in their central data center. And then you have regional data centers, right? And 85%, which is a partial edge. So edge is again a very confusing term. Depending upon who you ask what is an edge, you may get a different answer, right? And that's another thing which LF Edge is trying to do, to define a glossary so that everybody can understand what each terminology means, right? So here is a partial edge, right? And then you go in further down, and that's a smart central office, and that's your edge, okay? 97% of the operators plan on putting VNF functionality over there, right? And then you go further down, and we call it as a far edge. That's where your actual devices are. That's where your iPhones, that's where you're playing the video games, that's where your customer premises equipment are, and so forth. So this gives you an idea. And from original data center all the way to the edge devices, 20 millisecond or less, that's the requirement. And that's what's driving all the key requirements for the edge, which is high bandwidth and low latency. So that's where things are going, okay? So again, this is an LF Edge slide. So this is a little older slide. Those are the top. On the top, there are 5 projects. They are the founding projects in the Linux Foundation. There is another one, Fog Lamp, was introduced very recently. Again, I said it's a little bit older slide, and 60 plus members already. Now it's much higher. Okay, so a lot of people are coming in there. So there's a lot of interest, and everybody wants to go. So I'm going to talk about Akraino Edge Stack in this one. And before we go there, and here is the map. This is how all these different projects align. Akraino Edge Stack it covers this span from the telco cloud edge to all the way to thick and thin gateways, right? Home edge deals with IoT devices or home devices or the edge devices. The virtual Eve, which what we call it, is that deals with all your oil wells in the field they're running, and you have put the sensors and whatnot. And then on the left, you have different platforms and devices. EdgeX Foundry is an interoperability for the iOS device management. and remember earlier I mentioned the glossary, edge computing glossary. That is, they are trying to define the terminology so that people, when somebody says what is an edge, everybody understands what an edge is. What is a far edge? What is a near edge? There are too many partial edge. There are too many terminologies being thrown out, and that's the goal of edge computing glossary. Okay. So having said that, Akraino edge stack. So Akraino edge stack, it's the main. It's targeted towards telco and enterprise and industrial IoT use cases. What it is doing is it's trying to drive to a fully configurable, complete production-ready deployment. Essentially, think of it as a vertical stack. Right? And it facilitates and it uses the upstream projects, open source projects. It integrates them, it facilitates the integration with them. So I'm down to my few minutes, so I'm going to start skipping through some of the slides. So essentially, that's the critical mission of Akraino. There are three types of blueprints. One, we call them integration blueprints. That's where multiple vendors and providers come in and they build their edge use cases. And those are integration, right? We require minimum of two parties to come along. So it's not like just one company can put a blueprint. It will not be accepted. So minimum two, maybe more vendors or providers or whatnot, they have to come together and provide an integrated edge solution. Then we have a feature project. Feature projects are which span across the blueprints, where different edge use cases can leverage those features. And then we have a validation project. So there we provide a platform, a framework for different edge use cases to be validated. So once you validate here, you can pretty much take it and consider it as a deployment ready. This is an AT&T slide. I stole it from them, but essentially it pretty much shows you the same thing. The centralized cloud, you have in tens. Once you start going toward the edge, it's at thousands, and once you go towards the far edge, it's millions. So the latency requirement, as you go closer to the device, on the left-hand side of the slide is less than 2 milliseconds, and then as you start getting towards the right-hand side, the latency requirements starts to go higher. Okay. Here is another. That's by the way, this is a network cloud use case which Akraino is addressing, right? And AT&T is getting ready to deploy it in their production networks. This is the second use case, which is for IoT, enterprise IoT. So in here, what you have is at the top, you have different cloud automation, network automation, and IoT automation at a higher level. Underneath, you have different use cases, and at the bottom, you have devices, right? So you're orchestrating from the top. You have a central enterprise data centers, which are dealing with, and then you have a southbound devices, IoT devices, sensors or whatnot, and you're managing them. So that's the second use case which Akraino is addressing. Here is a good way to see what Akraino brings. So typically, without Akraino, right, when you're building an edge solution, when you're a provider, you're getting ready to deploy an open source based solution, you have a lot of choices. You have ONAP, Airship, OpenStack, and whatnot, Kubernetes. You make a decision as to what your deployment is going to look like. So think of those as ingredients, and the recipe is what you want to deploy. So you will take those different pieces, you will test it, you will put your CI/CD system together, you will run through all of that, and it takes you months and months to actually get it deployment ready. What Akraino does is it takes those ingredients and builds multiple recipes, and those recipes are called blueprints. So in there, in a given recipe, it will pick that's going to use Kubernetes, Airship, or whatnot, and it goes to all the way from hardware all the way to the top level. So it will actually specify that single rack, multi-rack Dell computers or ARM-based computer or Intel-based processor. It goes into that much detail in terms of specifying the hardware. It specifies which operating system, which orchestration, SDN-based, non-SDN-based, and whatnot. So once you have that fully tested vertical deployment stack, it's pretty much production ready. And there is a CI/CD system, and there is a validation framework, which I touched earlier. So it runs continuously. So therefore, when you pick a blueprint and you say, okay, this blueprint solves my edge use case, you can pull it and deploy it. Somebody has already done it for you. Somebody has already tested the whole ingredients for you as an end-to-end complete solution. That's what Akraino brings. Right. Here are a few blueprints which were part of the release 1, which went out back in June or July, and we're getting ready to release release 2. A lot more blueprints will be coming. Release 2 is coming in November, next month. Okay. So here's the Tungsten fabric and Akraino. So if you notice in the middle, you will see a Tungsten fabric. This is called provider access for edge. This is a lightweight deployment. There is no OpenStack in this. This is strictly Kubernetes based, very lightweight for very large scale deployments, lightweight deployments, right? So this is Red Hat, Intel, Juniper, and I believe there are 1 or 2 other companies together working on this blueprint, and this was part of release 1 of Akraino. Here is Network Cloud blueprint. This is what I mentioned earlier. This is the AT&T blueprint, and here they use Calco, SRIOV, OVS, OpenStack, and Kubernetes. Right. So what we have done is, as a Tungsten fabric community came along, and a lot of people want this blueprint with Tungsten fabric rather than Calico or OVS. They want not L2 based, but they want L3 based, and they want to take advantage of all the features which I talked about earlier. So what we have done is we have taken those components out and replaced them with a single SDN controller. So now it does everything for you, and it manages all the workloads, all the policy framework, all the edge computing examples which I was giving. You get all of that with this blueprint, and that's what this is getting ready to be released next month. So it'll be available if you want to test with it, you want to play with it. Next month it'll be available at Akraino portal. You can pull it down and play with it and test it. And essentially what it does is you have original controller which deploys the edge side. Underneath it uses Airship, and Tungsten fabric help to deploy it. But essentially whatever Network Cloud does, we pretty much follow that. And in this case, Airship is the way things get deployed. This is my, I think, last slide. This is another use case. This is with the Mobile Edge X, right? This is for the mobile devices and your gaming and virtual reality. So this is there is a distributed machine engine, and that's the engine which deals with the devices, authenticates the device. If you have played Pokemon Go or whatnot, or if you played any games on your devices, authentication when you log in and so forth, that's what DME does, and it looks at it how many players are coming on board or how many workloads are coming on board. Based upon that, the Cloudlet Resource Manager that launches the workloads depending upon the need and the load, and Tungsten Fabric manages the VRouter forwarding plane, and it's integrated with Tungsten Fabric agent, which I talked about earlier, and the Tungsten Fabric controller. So essentially, the CRM talks to one controller, talks to another controller when they're getting ready to place the deployment, and this is how they take full advantage of all the capabilities which are available in Tungsten Fabric. So that's how Tungsten Fabric is playing in a network cloud in a telco world. This is how they're playing it in the mobile workloads. And earlier I mentioned the lightweight Kubernetes based. And there are few other blueprints which are in the works, which will address the IoT workspace. Right? So this is how Tungsten Fabric and Akraino work together to bring essentially the edge use case. So here is a link. If you want to play with Tungsten Fabric, you can just go pull it up, pull it down. It takes 15 minutes. That's what the link says. It will take you 15 minutes to deploy it, and you will have the full deployment up and running once you follow. There are a few steps you follow, and you will have it up and running, and you can play with it, you can test with it, and have fun with it. And I want to thank you for giving me this opportunity to talk to you, and you patiently listened to me without harassing me. And now I can see the guy is ready to harass me. Go for it. Have a shot.
Sure, Sukh. Thank you for your great presentation on Akraino as well as on the earlier on the Tungsten Fabric. I would like to know something about, since you are talking about the tags and connecting tags, is it a name data?
Sorry?
Indian, is it an Indian name data?
It's your strings. It's just a name. You can call it a precautious deployment.
No, what I'm saying is the policy manager, does it implement name data networking, which is Indian they call it?
Can you bring a little bit closer? I'm having a hard time hearing you.
So there is something called name data networking.
I don't know what that is. I've not heard that term.
Okay, that's
maybe you can educate me offline.
Okay.
Maybe I'll learn something from you today.
Thanks.
But essentially it's a tags. You can. So what we have done is we have defined some default tags like deployment, site, and so forth, and network. Those are like common keywords which we have defined, which you can use it. On top of it, you can define anything. You can call it a precautious deployment or Sandy's deployment, and you can say precautious deployment can talk to Sandy's deployment. So you can build your own tags and simplify the whole deployment. So that's how it works essentially. So I'm going to hang around, so feel free to grab me. I'll be more than happy to answer more questions.
Thank you.